Okay, last time we did the normal distribution, section 6.2, and then I sent out something by email as an example problem that I was not able to get to in class. Everybody get that email? Did you open the attachment and read it? Well, then if you ask for help, I'm going to say, just read that. All right? Any questions over normal probability problems? It can be a little tricky the first time through it, and I know it went really fast in class last time, so just kind of expect that you're going to struggle with it a little bit, but that thing that I posted out there will help. It's an example of using the inverse norm function. It's not an example of using the normal CDF function, but you just need to work on that. Feel free to, there's been a few people that have clicked on the Ask My Instructor button already. Morgan was one of them. And that's works best for both of us, right? If you just email me and say, I don't know how to work number 3, well, I can't see what you tried. But if you hit Ask My Instructor, then I can see what you've entered and see what exactly the problem is. So feel free to use that, and we'll get you through those. The review sheet will be posted this afternoon, and you can download that and get it completed by Monday. Monday we'll go through it as review. Wednesday test. Everybody going to be ready? All right. So today is the binomial probability distribution. And this is section 6.3. So by way of motivation here, remember this tree diagram? What was our scenario here?
Flipping a coin.
Flipping a coin. H's and T's were heads and tails. And how many times did we flip it?
3.
3 times. And we set up a probability distribution. Let me say it here. X equal number of heads in 3 flips. Right? So what we developed this probability distribution last time. Today what we're going to do is show that, well, that actually is something called a binomial distribution. The number of heads could take on 4 possible values. A 0, 1, 2, and a 3. Now, look back in your notes real quick and remember what these probabilities were. We used this tree to figure out what those probabilities were. So I want to write them down, but I don't want to just write the numbers down yet. I want to write down what was multiplied in order to get each of them. So this top one, x equals 0. Which branch of the tree is that? That's the bottom branch. That means tails, 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 with the probability of 0.45, 45, 45 all the way across. Remember, this was not a fair coin, it was a biased coin. Right? So I can write that. You can find the probability for any branch by doing what along the branch? Multiplying, that's the multiplication rule. Tails on the first one, and tails on the second, and tails on the third means multiplication rule. So this one is 0.45 cubed. Right? What's the top branch? Hello?
0.55 cubed.
0.55 cubed. Good. 0.55 cubed. Right? What's this branch? I'm sorry, this value of x. X equal 1. Well, remember what we did? We said, well, we have to figure out all the branches that have 1 H and 2 T's in them. Right? And how many branches are there like that?
3.
3. 1 H and 2 T's. So I can't go up there because I've already got 2 H's. So here's 1 H. I can only get the T there. So here's one of them right there. So this is H, T, T. The probability of that, and that's the probability that x is 1, is what? multiply the probabilities along the way, and you got 0.55 times 0.45 to the, what's the exponent?
Squared.
Squared. Right? So I'm going to write that over here, 0.55 to the first, 0.45 to the second. But now there's 3 branches. So I can put the multiplier of 3 out front there. Right? Now see if you can do this one in this kind of notation. Really good frown on your face.
I was wondering why.
Wondering why what?
Why was there 3?
Why was there 3?
Yeah.
Good question. That 3 is there because that's how many branches there are that give me 1 H and 2 T's. And I listed one of them here, but let's find the other ones. Here's a tail, head, tail. So that branch gives me 1 H. So it also is a 1. Right? And then tail, tail, head. So all 3 of these have the same probability. So there's 3 of them. So I can add these 3 probabilities together, which is the same as multiplying by 3. So that's where that 3 came from. Now, how many branches have 2 H's and 1 T? 3. And in fact, that's the only 3 that are left. We've done the top one, we've done the bottom one, we've done these 3. Now the only 3 left are 2 H's and a T, 2 H's and a T, 2 H's and a T. Right? Well, what are those probabilities? This is H, T, H. That probability of a 2 is what? How many times did I use 0.55? Twice. So 0.55 squared times 0.45 to the first. And now I got 3 of those. So over here I can write 3 times 0.55 squared times 0.45 to the first. Yeah.
Wouldn't the 0.45 cubes be switched with the 0.55 cubes? Because if x is the number of heads and flips, you can't have.
Yes.
Is that was confusing?
Thank you. I did that on purpose just to see if you were paying attention. One person was. Anybody else notice that? Several of you? Yeah, sure. Now you say you do. No, I'm sorry. I did have that backwards. This was 0 heads, which means they were all tails. So it's 0.45 cubed. And this one's all 3 heads, so 0.55 cubed. Okay? Now, just to make this interesting, I'm going to move that 0.45 cubed over here and put 0.55 to the 0 power in front of it and a 1 in front of that. What is something to the 0 power?
1.
1, right? That's algebra class. Down here I can put a 1 in front of that without changing it, and I can put a 0.45 to the 0 there. Then they're all in the same form. Some coefficient out front, 0.55 to some power, 0.45 to some power. And what are those powers? Look at these numbers for x, and where do you see those numbers as exponents? 0, 1, 2, 3. So what I have is 0.55 to the x power. Then what's the power on 0.45? Now we'll see how good you are at finding out formulas for patterns. It starts at 3 and goes down to 0. When x is 0, this power is a 3. When x is 1, this power is a 2. Anybody have an idea? How many flips did we do altogether? 3. If 0 of them are heads, how many are tails? 3. if one of them is heads, how many are tails?
2.
2. So if I take the total number of flips minus the number that turned out to be heads, I get the number that are tails, right? So how many flips total were there? 3. So this is 3 minus x. Right? So what I've done is I've come up with a formula for the probability that fills in this table, except I'm missing that coefficient out front. And that coefficient turns out to be what's called the binomial coefficient. And in our calculator's notation, it's written like that. Which is, let's see, let me use this space over here. NCR means combinations of n things taken r at a time. So I'm just going to write combinations. Now, I really don't care that you know the formula for this combinations because this coefficient is built into the calculator, but I want to give it to you because it's cool. So NCR is equal to n factorial over x or r factorial n minus r factorial. So what does factorial mean? This is a mathematical symbol, n exclamation point. And I'll give you a hint, it does not mean I'm excited about that n. N! Yeah.
Like if you had the number 5 as n, you would do 5 times 4 to 2 times 2.
Exactly. That's factorial. So factorial in mathematics means take that number times all of the integers down to 1. So if it's 5 factorial, it's 5 times 4 times 3 times 2 times 1. If it's 3 factorial, it's 3 times 2 times 1. So if I want to know how many ways or how many branches there are with 2 heads and 1 tail, then I've got 3 flips, 2 of them to be heads. So combination of 3 flips, pick 2 of them to be heads, right? So I would have 3 factorial over 2 factorial times 3 minus 2 factorial, and that's 1. 1 factorial is just 1. And by definition, 0 factorial is also 1. Okay? And there's no real easy way to see why that's the case. It just kind of has to be defined that way. But what is 3 factorial? 3 times 2 times 1. That's 6, right? What's 2 factorial? 2. 2 times 1. So 2, and then 1 factorial is 1. So 2 times 1, 6 over 2 is 3. There's 3 branches with 2 heads. Right? Why do we need this? Why can't I just count the number of branches?
What if we had a huge amount of branches?
What if I flip my coin 10 times? Finish this tree for 10 flips. This is 3 flips, finish it for 10. That thing gets big in a hurry. How many final branches would there be if I flipped my coin 10 times? Well, let's see. I flipped it 3 times. Each flip has 2 possible outcomes. So there's 2 outcomes of the first flip, 2 outcomes of the second flip, 2 in the third. That's 2 times 2 times 2. Or 2 to the third, which is 8. 8 branches. If I flip it 10 times, it's 2 to the 10th. Yikes. Does anybody besides me have 2 to the 10th memorized? I only have it memorized because I did this morning already. It's 1,024. So if I ask you on a test to finish this tree for 10 flips, you just laugh and go on to the next one. You can't do 1,024 branches, right? So we need things like this to tell us how many branches would there be with 8 heads and 2 tails if I flip my thing 10 times? Well, I can't count branches and go, oh, that's a whole bunch. How many would there be? Well, I can do it on my calculator. I can enter, and let me turn on the projector, which I forgot to do earlier. get out your calculator. And that has to warm up a little bit. And I'll dim this front light. And if you push, put the number in that you want. So right now I'm asking for 10 flips, combinations of 8 heads. How many branches are there with that? The way you use your calculator is you enter the 10. Oh, my calculator's up now, so I can do it with you. Clear my screen. Put in the 10. Then push the math button. Then go over to PRB, and you'll see the NCR there as the third one down. Everybody find that? Go down to NCR, press enter. So now on your screen you have the number 10 and then NCR, and now you want to enter the 8. And then press enter. So 8, and enter. And it tells me that there's 45 out of the 1,024 branches. 45 of them have 8 H's along there and 2 T's. Okay? So that's known as the binomial coefficient. And it's the coefficient out front in the probability statement. So in real general terms, the binomial probability distribution function is P of x equal NCR, NCX. The calculator uses an R, but it's whatever number, however many heads you want, and I'm calling that x. So NCX times the probability, where does 0.55 come from? That's the probability of what? Heads on a single flip, right? So we call that P. And then we raised it to what power? The x power, the number that I want the probability of. Now where did 0.45 come from?
The number of T's, or the probability of a T.
The probability of tails, right? So instead of heads and tails, I'm going to start saying successes and failures. So we've defined heads as success and tails as failure, right? Well, how did I get 0.45? I did it in my head, but what did I do to get 0.45? 1 minus 0.55. So this is 1 minus B. And then finally, what goes the exponent there? It's 3 minus x if you flip it 3 times. What if you flip it 10 times? If you flip it 10 times, it's 10 minus x. If you flip it n times, it's n minus x. So it's just always the number of trials minus the number of successes. Okay? So I just used a new word on you, trials. Each flip of the coin is called a trial. That's not a new word. We did that before, right? We talked about independent trials and dependent trials. Are these trials independent? Yeah, they are. Because when I flip that coin the second time, the probability of heads is still 0.55. It doesn't change. If the probability stays the same from trial to trial to trial, then they are independent trials. If they change, then they are dependent trials. Okay? And this won't work.
What did in your example, the 10 C8, what did the 8 stand for?
That's the number of successes.
Oh, okay.
Number of, in this case it was heads, number of heads, and number of trials. Okay? So now, this is the binomial probability formula. And there may be some homework problems where they say, they ask you for different pieces of it. Fill in the pieces and then multiply it all together, right? But your calculator will compute this automatically all in one step. So let's see how to do that. So I don't think I need the tree anymore, so I'm going to get rid of the tree, so I have some room here. this number, before we go to the calculator, I want you guys to give me these 4 numbers as decimals. Alright? So, Logan, I want you to do the top one, and Delaney, you do that second one, and Naomi, you do this third one, the one with the 2, and Jory, you do the bottom. Okay? I'll give you those 4 numbers as decimals. And then we're going to go to a calculator and confirm that it gives exactly the same thing when we do it with the function. You got the first one?
0.091125.
091125. Okay? And who did I ask? Delaney?
0.334125.
125. Okay? It's kind of hard to read when I have that projection on there, but I need that. So. And you were next, right?
Yeah, 3375.
3375. Okay? And the last one?
0.0748.
0.0748. Something's wrong.
Oh, it should be 0.0749. Sorry, I didn't round that right, but,
It's still wrong.
okay.
I don't know if that's the one that's wrong, but something's wrong in there. And why do I know something's wrong?
Just add the 1.
It doesn't add to 1. If it's a probability distribution, then it has to add to 1. So something's wrong.
I missed a number on mine.
So this one's wrong?
Yeah,
Okay?
it's 0.408375.
408375. Okay? That helped. It's still not there though, are we? Because this adds to about 0.7, and that's only 0.1, so that's 0.8, and that's only about 0.1. We're not quite there yet. And Jory, I'm pretty sure it's that
I
number.
know, I'm trying to think of what.
All you need to do is 0.55 cubed.
Oh, okay, I added the 0.45 in there
Okay, that had a 0 power, which got
too.
erased.
Yeah, that's what I was wondering.
Sorry.
Okay.
So I set her up for failure. But it made a good example to look at your thing and realize something's got to be wrong.
It's 0.166.
0.166, give me
375.
375. Okay. All right. So we're comfortable with those numbers. They do now add up to 1. I just guessed, but they look about right. Now let's go to the calculator. And in your calculator, you have the binomial distribution function already programmed into it. Just like you had the normal distribution function in it, which we did last time. So you're going to find it in the same place. Where do we find distribution functions? You're going to, second function, DISTR, which is on the vars button. So second function, vars, and it comes up with distribution. You'll see the normal PDF, the normal CDF, and all those things. And I don't see anything that looks binomial, so just start arrowing down. And there's 2 of them. There's a binom PDF and a binom CDF. Now, when we did the continuous distribution, the normal, I said don't ever use the PDF, right? But this is a discrete distribution, and the PDF gives us the height of the bar above a point. And that, in a discrete distribution, that is a probability. In a normal distribution, the height above a point isn't a probability in a continuous distribution, so we don't ever use it. But here we do want it. So this is, I'm going to extend this statement here. This probability is computed on the calculator as binom PDF. I sure wish I had a better marker. And the thing, you enter 3 things into the binom PDF. You enter N, and then P, and then X. So, for this problem, what is our N?
Three.
3. equal 3. So whenever you realize that, oh, this is a binomial problem, first thing to do is identify n and identify p. What is p? Well, p is the success on a single, the probability of success on a single flip or a single trial. And that is what here? 0.55. So into my binom PDF, and I'm going to do it up here on the calculator rather than write it on the board. I'm going to select binom PDF, and I'm going to enter 3 for n. I'm going to enter 0.55 for p, and I'm going to enter, we're just going to work down through this whole table, x as 0 for the first one. So put 0 and then press enter. 0.091125. Exactly the same number that we got when we did it the hard way. Now go ahead and do the next one on your own. And by the way, you can hit second function enter and it'll pull up the last thing you did, and then you can just arrow back over the 0 and change it to a 1. Isn't that cool? Saves you going through all those menus and trying to find it again. Question?
What was that shortcut you just said?
Second function enter. It pulls up the last thing you did. And then you can use your arrow to go change the 0 to a 1. Okay? So you should have gotten exactly what we have here, 0.334125. So from now on, when you're asked to do a binomial probability, you can go right to your calculator and do binom PDF rather than use this formula. All right? It's a whole lot easier. But I want you to see what the calculator is doing. This is what it's doing. It's taking p to the power of number of successes. It's taking 1 minus p to the power of the leftover trials, the ones that weren't successes, so these are failures, times the number of branches or the number of ways that that can happen. Okay? Now, let's do some, let's complicate things for you a little bit. That's always my favorite thing to do. What's the probability that I flip this coin 3 times and I get less than or equal to 2 heads? Less than or equal to 2 heads. What is that saying? What values, of the possible values, which ones are less than or equal to 2? 0, 1, or 2, right? So what that's saying is you can make that statement true by being here, or here, or here. And I just said the word or. So what does the word or mean? Add the probabilities. So if I add those 3 up, then I'll have the answer to that, right? Anybody have that?
0.833625.
0.833625. Right? But a less than or equal is cumulating the probabilities up to the 2. That sounds like a CDF function, cumulative distribution function. So go to the binom CDF, second function vars, and arrow down to binom CDF, and enter 3 for n again, comma, 0.55 for p, comma, the number I want to accumulate up through, and that's a 2. And you get the same number, 0.833625. So, in summary, here's what we got. We got that the probability that x is equal to some number little x, so this is a capital X equal some little number where this is just a number. That probability on the calculator is binom PDF in P and that little x. Probability that x is less than or equal to some little x is equal to binom CDF at n p x. Okay? All right. Now, let's do, let me change this. Let's make it greater than or equal to 2. What's the probability that I flip this coin 3 times and I get greater than or equal to 2 heads? Another way that that's often said is at least 2 heads. What's the probability I get at least 2 heads? Well, in terms of just adding up probabilities, which ones am I going to add? 2 and 3. All right, I'm going to add those. So go ahead and do that. It's going to be 0.574 something, right? Go ahead and read it to me.
Like 5748.
Or 8.
I think I'm missing some decimals. Oh, yeah.
Yeah, it probably has more accuracy, but. I got it?
You need for a 7.5 at the end.
Yeah.
Just 7.5?
Yep.
Okay. Thank you. Now, I can't do that straight with my calculator. My calculator only has these 2 binom functions in it. It has the binom PDF to calculate exactly equal to some number. It's got binom CDF to compute less than or equal to some number. It doesn't have one to compute greater than or equal to some number. But here's where you can take advantage of that complementary events rule. All right? Remember, the probability of A is equal to 1 minus the probability of A complement. So now we've got to figure out, well, what's the complement of being greater than or equal to 2? If you didn't get at least 2, what did you get? Less than 2. You either got 0 or you got 1. Now, since it's a discrete distribution, I want to write the complement in terms of a less than or equal, because that's what my calculator handles. So this is equal to 1 minus the probability that x is less than or equal to what? 1. Okay? So notice that to get from here to there, you subtract 1. When you do the complementary event, to turn that thing around where your calculator can handle it, you got to subtract 1 off. That's a really common mistake, is to leave a 2 there and do the binom CDF with the 2, but then what you're getting is these 3 probabilities added together and not these 2. So the way to do that on your calculator, oh, by the way, this probability we could have done just by looking at this and saying, well, that's these 2 added together, right? Because that's, yeah. I got lost there into my greater than or x less than or equal to 1 is these 2 added together. So these 2 are complementary events. These 2 circles are complements, right? So what I can do in my calculator is I can put in my 1 and my minus. Then I can go second function vars and go down to binom CDF and enter n, which is 3, 0.55 for P, and 1. and I get 5, 7, 4, 7, 5, 5, 7, 4, 7, 5. And Marianne, you just got the greatest expression on your face. It looked like this. What does that mean? Is that what you're asking? How in the heck did you do that? Okay, what is it? What part threw you? Anything in particular?
I entered exactly what you did. But,
Oh, you didn't get the same answer? Check that you got CDF and not PDF. You already checked that? Did you get 3, 0.55 and a 1? Did you do the 1 minus it up front?
No.
There you go. Okay, so now you can do 1 minus the last answer and you should get the right thing. Okay? Now where you'll see this a lot of times, they'll say things like, if you flip a coin 10 times, what's the probability you get at least 1 head? And that means you get 1, or you get 2, or you get 3, or you got a lot of things you have to add up there. Or you can just, well, complementary event. What's the complement of at least 1? If you didn't get at least 1 head out of 10 flips, you got what?
No, I just said 10, but that was wrong. I
Oh.
said you got tails. Yeah.
That means you got 10 tails, right? You didn't get any heads. The complement of at least 1 is none. So then you're just finding 1 minus the probability of getting 0. And that's a whole lot easier than adding up the probabilities for 1 and 2 and 3 and 4 and so on. So you'll use this complementary event thing with your binomial CDF and PDF functions to figure out problems like that. Okay. Now let me dim this for a second. And we got a couple more concepts we have to get out of the way. And then if we have time left, we'll work one of the homework problems. So let me turn that light back on. Now, not every problem is a binomial probability problem. Right? That's always the danger, is when you teach students a new type of problem, and they want to apply that to whatever the scenario is, right? It's like you gave them a hammer, now they're looking around for a nail, right? And they want to pound a nail in. Well, it only works in certain kinds of problems. They have to be a random variable that is binomially distributed, right? So here are the conditions that make it binomial. Now the book lists 3 conditions. I list 4, so I number the first one 0. And it's really not a condition, so the book is right, but I like to write it as a condition because that's what you should think of first. In order for it to be binomial, the first thing that you have to check is, are we counting the number of successes in a fixed number of trials? Okay? So, counting successes in a fixed number of trials. Okay? If it's not a problem that's having you count the number of successes in a fixed number of trials, then it's not going to be binomial.
Would that just mean that it's a discrete possibility or probability?
Yes, exactly. So these are counting numbers, right? Counting number of successes. Here's an example of not having a fixed number of trials. What's the probability that what I'm going to do here is I'm going to flip this coin until the first heads occurs, right? It could occur on my first flip. It maybe won't happen to my second flip, or maybe not to my third flip, or whatever. What's the probability that X is a 1 or 2 or 3 or whatever? I got tails, so it didn't happen on my first flip, right? Well, is that binomial? I'm looking for successes, a success being head, but I don't have a fixed number of trials. I'm not setting in advance I'm going to flip it 3 times. I'm saying I'm going to flip it until something happens. So that's not binomial. Okay, second condition. Each trial this marker's backing me off. Each trial has exactly 2 possible outcomes. Heads or tails, male or female, success, failure, right? If you give a survey, it can be a question with 2 outcomes, yes or no. You know, do you agree with this statement, yes or no? If you give them a maybe, yes, no, maybe, it's not binomial. And now you got 3. But a lot of times we have problems that aren't binomial, but we can turn them into binomial. Because we can say, you know, like one of the problems in the book talks about race, and it talks about the breakdown of Hispanic and white and black and Asian or whatever, and then it says what's the probability that you get 3 Hispanics in your sample of 10 people or whatever. Well, then you break it down to they're either Hispanic or they're not, so it becomes binomial. Okay. So be careful of that. That's kind of the only trick with that 2 possible outcomes. The third or second condition, starting at 0, is that the probability of success on each trial, which we call P, remains constant. Right? So when you flipped the coin the first time, the probability of heads was 0.55. When you flipped it the second time, it was still 0.55. And it didn't change. But if I'm sampling from cards, and I'm sampling without replacement, the first time I deal a card, the probability of getting a red card is 1/2, 26 out of 52. But then on the second card, if I sample without replacement, I don't have as many red cards still in there, so the probability now changes. So that would violate that condition. And usually this comes down to that question, are you sampling with replacement or without replacement? The third one is mathematically equivalent to the second, and that's that the trials are independent. So you don't really need to check 2 and 3. You can check one of them, and if one of them is met, then the other one by default has to be met, and vice versa. If the probabilities remain constant, that means they're independent. If they're independent, that means the probabilities are staying constant. Okay? So, whenever you see a problem, and you read the scenario of the problem, and it sounds like, oh, we're counting the number of successes in a fixed number of trials, then you say, well, this might be a binomial problem. But it's not a guarantee that it's binomial. It might not be. You have to check the rest of the conditions. Okay? One other definition, and then we'll practice a little bit. The mean of a binomial distribution, the mean of the random variable x, if x is binomial, is simply n times p. And if you think about that for a second, that makes intuitive sense, because the mean of a random variable is another way of saying expected value. If I flip a fair coin 10 times, how many heads do you expect? That's not a trick question. If I flip a coin 10 times, how many heads do you expect me to get? 5. And what's P? If it's a fair coin, 0.5. Probability of success on one flip, right? 0.5 times 10 is 5. So the expected value is just how many times you flip it times the probability of success on any one flip. Okay? The standard deviation isn't quite so intuitive, but here it is. It's n times p times 1 minus p, all under a square root. And it's just an algebraic definition, an algebraic derivation to come up with that. And I'm not going to take the time to go through it because I'm short on time. But these two formulas are in your book, and you will have to use them both on the online homework and on the exam next week. You'll have to know how to get mean and standard deviation. You can always do it the hard way. You can write out the distribution and put it in L1 and L2 and do that. But if it's binomial, you can get it real quick just from those formulas. Okay? Okay, I'm going to read to you a scenario here. And this is problem 643. It says the juror pool for an upcoming murder trial of a celebrity actor contains the names of 100,000 individuals in the population who may be called for jury duty. The proportion of the available jurors on the population list who are Hispanic is 0.4. So 40% of them are Hispanic. A jury of size 12 is selected at random from the population list of available jurors. Let X equal the number of Hispanics selected to be jurors. Okay, are we meeting the zero condition, counting the number of successes in a fixed number of trials? What's the fixed number of trials?
How many jurors?
It's the number of jurors. There's 12 jurors. Each trial is a selection of one person, right? Okay, so good. We are counting number of successes. We want to know how many Hispanics are there in this 12-person jury. Does each trial have exactly 2 possible outcomes? Now, don't think of the word trial as being the murder trial. This is a selection of one juror, right? Do they have exactly 2 possible outcomes? They're either Hispanic or they're not. Probability of success on each trial, is that remaining constant?
Oh,
No, it's not, because there's 100,000 people, and when you get one Hispanic going, but we can ignore this. We'll say this is okay if sampling less than 10% of the population. So if there's 100,000 people and I'm sampling 12 of them, I'm way less than 10% of the whole population, right? In other words, we're admitting that, yeah, the probabilities are changing, but they're changing so slightly that it really isn't going to affect the overall probability, so we ignore it. So we'll waive that one off if this is met, if we're sampling less than 10%. So some of the homework questions say, is it reasonable to use the binomial distribution? And that's what they're asking you to look at. Are you sampling less than 10% of the population? Okay? So technically, that problem is not a binomial problem because it doesn't meet that restriction. But since we're sampling such a small percentage of the population, we can ignore that and go ahead and use the binomial distribution. All right, that's all the time we have. So we will see you on Monday. Review Monday, test Wednesday. And you do have homework due tonight, so don't forget that.